Hello guys, a very good morning to all of you. Today in this particular video I will be talking about second order hybridization. So first of all, what is general hybridization? So according to normal hybridization, what we have studied from class 12, okay, so it is the intermixing of atomic orbital to form hybrid orbital like sp orbital, sp2 orbital, sp3 orbital. In the same regard we call it sp hybridization, sp2 hybridization, sp3 hybridization. But what is second order hybridization? So second order hybridization is the extension of your general normal hybridization. Okay, so according to which a fractional number of orbital is participating. Okay, so what if I tell you that hybridization of water, okay, we know the hybridization of water is sp3, but hybridization of water should not be sp3, it should be sp4. Again, the hybridization of ammonia should not be sp3, it should be sp3.4. Okay, so it sounds interesting, right? But trust me, the concept is also interesting. So let's get started. So before we discuss second order hybridization, let me discuss some important points from normal hybridization so that we can understand second order hybridization more easily. So we generally talk about sp3 hybridization, sp2 hybridization and sp hybridization. Generally we take three examples to understand this. Okay. Now in sp3 hybridization, what is the bond angle between two sp3 hybrid orbital? It is 109.5 degree. In case of sp2, this means the angle between two sp2 hybrid orbital is 120. It is from for sp it is 180. In case of sp3, what is the percent s character? This is your bond angle. So what is the percent of s character? For sp3 it is 25%. It is for sp2 it is around 33%. For sp it is 50%. Like in the same way, what is the percent of p? It is 3 number of p orbital, that is 75%. Here it is around 66%. It is for sp it is 50%. So as you can see, so one thing we conclude over here is, see this bond angle and percent s and percent p. What we observe? As the bond angle increases from 109.5 to 180, the percent s character is also increased in the same manner. Likewise, as the bond angle is increasing, the p character is decreasing. That means we can say that the bond angle is directly proportional to percent s character as inversely proportional to percent p character. And this is the key point to understand our second order hybridization. So this is to be remembered, that bond angle is directly proportional to percent s character and bond angle is inversely proportional to percent p character. Okay, so generally hybridization means what? Hybridization tells us that a particular orbital is comprises of how many percentage of which orbital. Like say for example for sp3, that means this orbital is made up of 25% of s orbital and 75% of p orbital. Okay, so now that hybridization depends upon this bond angle as this one. So bond angle is directly proportional to percent s character and inversely proportional to percent p character. Again I am telling, this is the key point from where we can discuss our second order hybridization. Okay, now let me discuss another important term, hybridization index. So what is hybridization index I? For any hybridization SPI, so this is your hybridization index. So for any hybridization SPI, so I, where I is equal to number of p orbital to the number of s orbital. This is a ratio. So what is I? So this is I. The hybridization index is nothing but a fraction. So this is so this is I, what is the, it is the ratio of number of p orbital to the number of s orbital. Okay, so say for example for sp3, What should be the hybridization index? So number of p orbital is 3 and number of s orbital is 1. For s, so that is equal to 3. So for sp2, I is equal to 2 by 1 is equal to 2. For sp, I is equal to 1 by 1 is equal to 1. So as you can see, the number of s orbital is always 1. Okay, that's why we can say that the hybridization index is nothing but the number of p orbital involved in a particular hybridization. Okay, it is a trick point of view. You can remember the hybridization index is equal to number of p orbital in a particular hybridization, but it is actually, this is the ratio of number of p orbital to the number of s orbital. Okay, you can say either we can say number of p orbital and number of s orbital, or we can say fraction of p and fraction of s also. For sp3, what is the fraction? This is a fraction of p to the fraction of s. So what is the for sp3, what is the fraction of p orbital? 0.75. What is the fraction of s orbital? 0.25. Again you can get the same value as 3. Okay, so what we conclude, what we know from hybridization index is basically it is the fraction, it is the ratio of number of p orbital or fraction of p orbital to the number of s orbital to the or fraction of s orbital. Okay, so from trick point of view we can remember it, the hybridization index I is equal to the number of p orbital, as the number of s orbital is always 1 from each case. Okay, now there is a formula from which we can start our second order hybridization. Okay, that relates the whatever the bond angle we discussed, the ideal bond angle of hybridization, we can find it out mathematically also. There is a proper, we can get exact 109.5 for sp3 hybridization. How it is? So there is a formula, cos theta is equal to minus 1 by I. What is I? I is nothing but what I discussed just before. This is your hybridization index. Okay, so let's find it out for sp3. Okay, so this is formula to find out the bond angle. Okay, where the theta is the angle. Okay, so for sp3, what is the I value? This is 3. Let's put cos theta is equal to minus 1 by 3. That means theta is equal to cos inverse minus 1 by 3. And if you calculate it, you can calculate it by your advanced calculator, scientific calculator. You can find out exactly this is your 4.8 or is equal to, you can say 109.5 degree. Okay, you can find out for sp2 also. sp2, so cos theta is equal to minus 1 by, or I is equal to 2. So in that also, sorry, the theta is equal to cos inverse minus 1 by 2, and you get exactly 120. Same sp lagi, so for sp also you can find out the angle. So theta is equal to same way, this is cos inverse, you can find out very easily, like we need not do not need any calculator for calculation for the sp1. So how? This is cos theta is equal to minus 1 by, so this is, so cos theta is equal to minus 1 by 1, so this is equal to minus 1. Okay, so the for what value of theta, the cos theta is equal to minus 1. So we know the cos 180 is equal to minus 1, so theta is equal to 180, and we know for angle for sp hybrid orbital is 180. So we can find out the exact or bond angle from once I know the hybridization index. Okay, so that means once I know what type of hybridization it is, then I can easily find out that what is the bond angle between two hybrid orbital. Okay. Okay, one thing, one conclusion, what we conclude from this one, like for sp3, the exact bond angle is found to be 109.5. For sp2 it is 120, and for sp it is 180. That means for every individual hybridization there is a fixed bond angle, and vice versa. If you alter this bond angle, okay, then again then also your percent s and percent p alter. This is closely related. Okay, so if you change the bond angle, then the hybridization is also changed. So for this is to be listen carefully. So any molecule having the bond angle similar to the ideal bond angle, okay, then the hybridization of that particular molecule is exactly the same hybridization. So what do I mean this? So for sp3 bond angle is 109.5. So any molecule having the bond angle 109.5 have the hybridization exactly with sp3 hybridization. Okay, but in case any molecule differ from the ideal bond angle, that is deviated from ideal bond angle, in that case you cannot say the hybridization of molecule is sp3, because this tells out number of s or percentage and number of p percentage, or the fraction of s and fraction of p orbital. Okay, but there is a close related to the bond angle. We just discussed earlier that the number of is the fraction of the percentage of p orbital and s orbital is closely related to your bond angle. One is s orbital, s percentage is directly proportional to bond angle, and p orbital is inversely proportional to the bond angle. So if you alter this bond angle, you can eventually alter your hybridization. So in any molecule, the exact bond angle is not ideal. The molecule having a bond angle is not exactly equal to the ideal bond angle. In that case, we assign different type of hybridization, and that is known as your second order hybridization, and it is also known as isovalent hybridization. This is called your second order hybridization, and also called it is isovalent hybridization. Okay, so before we go to the examples, we just revise what we studied, what is discussed. We discussed that the percent s, so in any hybridization the percent s and percent p is related to the bond angle. So the percent s character is directly proportional to the bond angle. So if you increase the percent s, the bond angle automatically increase, and if you decrease the percent s, the bond angle automatically decrease. Again, the percent p is inversely proportional to the bond angle. That means if you alter the bond angle, increase or decrease, accordingly your percent p character also increase and decrease in the same way. Okay, then we discuss, so any molecule having the ideal bond angle is said to be the exact hybridization, that is a perfect hybridization. But in case the bond angle is not equal to the ideal bond angle, so in that case the general hybridization is not assigned. Instead, a different type of hybridization is assigned, and that is known as second order hybridization or your isovalent hybridization. So let's jump to the example what we give into the introduction, that is the hybridization of ammonia and water. Okay, this is very important. Okay, from these examples, okay, these things will be more clear. Okay, so now let's find out for ammonia. So how we get the sp3.4 hybridization? Okay. So we generally know the formula, the cos theta is equal to -1 by I, over I is not fixed, because we are going to find out the value of I so that we can assign the exact hybridization. Okay, so we know the exact bond angle. So what is the ideal bond angle for ammonia? Because the hybridization is normal hybridization is sp3. So what is the ideal bond angle is 109.5. Okay, but what is the actual bond angle? So it is around 107. Now you might be wondering that what is the reason for the decrease in the bond angle? We know that, okay, from BSc-PR theory. So this is a structure of ammonia. So from BSc-PR theory we know that lone pair bond pair repulsion is more than a bond pair repulsion. So this repulsion will more predominant. That means this lone pair push the two hydrogen towards down. So the initial bond angle of 109 now decreased by some extent, that is your 107. Now we know the bond angle, actual bond angle is not 109.5, instead it is 107. So we know the bond angle over here. So we can put it like this. So cos 107 is equal to -1 by I, because I need to find out the value of I. So if I calculate like this, so the I is equal to, okay, I is equal to -1 by cos 107. Okay, so you find out, you can find out by scientific calculator, you get exactly 3.4. So the value of I is found out to be 3.4. The hybridization should be sp3.4. Okay, In the same way, the hybridization of water, let's find the actual hybridization. So what is the second order hybridization of water? So it is the general hybridization is also sp3. So the bond angle should be 10.5, but this is not so. The actual bond angle, like the same way, okay, the actual bond angle is found to be 104.5. Again you can see the bond angle is drastically decreases. So initially your percentage of sp3, that means 25% of S and 75% of P. Okay, before this one, let's find out the exact hybridization. So cos theta is equal to minus 1 by I, because I need to find out. So we know the exact value 10.5 out. Like the same way, okay, so like the same way you can find out the I is equal to exact 3.99 or is equal to 4. As you can see, the hybridization index is found out to be 4. That means the second order hybridization is sp4. Now you might be wondering that is it possible to participate a extra p orbital hybridization? Because we know, okay, because we know there is only 3 p orbital available in the piece of cell. Okay, there is no fourth orbital available. There is no fourth p orbital is available in the particular piece of cell, because we know there are only three orbitals of p. There is a px, py and pz. So now you might be wondering, so where the fourth orbital is came? Okay, now one thing I just want to clear that that's why it is second order hybridization. This is not a general hybridization. So this hybridization means, it does not mean that it is a participate in the fourth p orbital. That is, in this hybridization there is a participation of fourth p orbital, the fourth p orbital and 1s. So it is not like that. So this sp4 means what? As the bond angle is decreased drastically, then we know initially discussed that percent p is inversely proportional, your bond angle. The bond angle is inversely proportional to the percent p. So as the bond angle decreases, number of p orbital, the fraction of p orbital increases. So initially it is 3, okay, initially it is 75%. At least as the decrease by at least 5 degree, that means at least 5% of p orbital also increase. That means it is 20% S and 80% P. That's why it is the ratio 4:1. That's why the second order hybridization of water is found out to be sp4. So make one thing clear. The sp4 hybridization or the second order hybridization does not mean the involvement of 4 p orbital and 1s orbital, because it is not possible, because there is no fourth orbital available in the piece of cell. So its only meaning, there is only single meaning of sp4. That means it indicates there is a bond angle deviated from our ideal bond angle. So the actual bond angle is not ideal. So it is the deviation from your ideal bond angle. That's why we can assign your second order hybridization. Like in the same way for the ammonia also, okay. So it is not possible to participate a fraction of fourth orbital. Okay, this is sp3.4. So where do you find where do you get another p orbital and you divide 6/4 ratio and we involve a fourth part in the sp3 hybridization to make sp3.4. It is not possible anyway. Okay, it is not possible in any way. That's why it distinguishes from your general hybridization. So what we clear from this discussion is, for any molecule having lone pair of electron or different substituents, then the hybridization is not ideal. In that case, we assign your second order hybridization, which allow us to understand that the bond angle is not ideal. Instead, it is decreased or increased by somewhat. Okay, in some extent. Okay, so I hope you understand that how the second order hybridization is different from your general hybridization, what we know from class 12. Okay, so I hope you found this video useful. So if this, then please share it to the student, let people know, okay, that let people aware of this kind of things. Okay, so there is, please, if you like this video, then like it and share it. Thank you.